Now we're interested in Gauss-Seidel for A is symmetric positive definite. Okay, so now this is not so easy to figure out just by yourself, but let's see, and then maybe you can understand how they re-engineer this. You sort of know where you want to work towards, and then you can go back and set it up correctly. So in this case, we don't write A is D plus L plus U, but I'm going to write this a little bit differently. I'm actually going to write this as D minus L transpose. You just note, sometimes they write these splittings as D plus L plus U, and then N has a negative L plus U. In this case, we just take the negative of it directly, D minus L transpose here, because A is symmetric, so the lower and upper triangular parts are the same. Okay, so if we now look at G for Gauss-Seidel, that would be equal to D minus L inverse times L transpose, like this. And really, again, the only reason why I look at this with these minuses instead of the way we did it before is that it saves us a lot of minuses later on. Okay, now we first make an observation, and that is that D itself is positive definite. And that's not really so hard to prove, and I actually just want to do it because you can see this definition of positive definiteness again. So A is positive definite. That means that X transpose AX is bigger than 0 for all X not equal to 0. Okay? Like this. So if this is true for all x's, it must also be true for the unit base vectors. So let's take an x equal to one of them, so EI. Then we have AEI is of course equal to the ith column of A, that's AI. Okay, but then AI transpose AEI will just be equal to the diagonal element AII, and that will be bigger than 0 because of A's positive definiteness, and this is true for all I. So we know that all elements on the diagonal are in fact larger than 0, and we're going to be using that later on, but I've always liked proving this a little bit. Okay, so now let's go and use the general convergence theorem, and we're actually going to show that the spectral radius of G is smaller than 1. Okay, now that turns out to be a little bit nasty, so instead we're going to look at the spectral radius of a similar matrix. And really, again, we want to get rid of these D's a little bit. So this happens very often. So instead, we're going to show that the spectral radius of D a half, G, D minus a half is smaller than 1. And we know that lambda G is lambda of this guy here because these two are similar, right? This is a similarity transform that you've looked at. And I know, of course, that the inverse of D to the half exists because D was bigger than 0, right? So D is positive definite, so I can actually take the inverse and I can take the square root. Okay, so let's call this thing G1. Okay, then we have G1 is D a half, G, D minus a half, like this. And that I can write, I'm just going to play a little bit with this, the identity minus L1 inverse times L1 transpose. And here L1 is also a lower triangular matrix, which is just this weighted L, d minus a half, like this. Okay. Right, so now we're going to look at the eigenvalues of G1. So let's take an eigenvector. Okay, so we take I and lambda such that G1 y is lambda y. Okay, so we just plug that in, so we have an expression for G1, and if we just plug this in, then we get I minus L1 inverse L1 transpose y is lambda y. Right, and that means that L1 transpose y is equal to lambda times I minus L1 times y, like that. So now we're going to play. We take the inner product of this with y. So we get y star, and this we often do when we deal with these positive definite matrices and we want to isolate lambdas. We can take these inner products, and you will see this trick very often. Okay, so we get this, and then we take y star with this right here, and then we get 1 minus here y star L1y. Okay. Now, this guy is some complex number. I don't know what it is. So let's say this is a plus ib. Okay. So if I look at this equation here, then this one, then I have the expression a plus ib is equal to lambda times 1 minus a minus ib. Okay, so I have in fact already an expression for lambda. So if we look at the magnitude of lambda, which we'd like to be smaller than 1, then we get, if you work this out a little bit, a squared plus b squared here, and I'll leave that up to you, divided by 1 minus 2a plus a squared plus b squared. And the question is this smaller than 1? And if it is, then we're done. Now, if this is smaller than 1, then what we really have to show here is that bigger than 0, right? And if this is bigger than 0, then we're done. So let's have a look. Okay, so we know that d minus a half, a d minus a half is equal to I minus L1 minus L1t. Now we want to say something about this 1 minus 2a, so we have to somehow relate this back again to L1. And we'll do this with a little bit of a roundabout way. Okay, now we know that this guy is symmetric positive definite. Okay, so I just tell you that it is, and you can check this for yourself. Okay, so that means that if we do y star times that thing, or the inner product, y star, like this y, then we have that this is bigger than 0. Okay, but what is this? Well, let's see, the first one just gives us y star y, so that would be 1. And then the second one gives us y star L1y, but we know that that's a plus ib. And then the third one gives us y star L1 transpose y. So when you think about this, this is just minus, or so you get minus a minus ib. Okay. But this is 1 minus 2a, and so with this, it means we're done. Okay. Now these, especially this last proof, which I think is superbly fun, is not something that you can think of easily. No, and so these are proofs that are really fun to look at. When you see them done, you see that you can. There's so many ways that you can play. Of course, in the final exam, I would never ask you to do this within just an hour or so, or 45 minutes. But I hope that by looking at these convergence proofs, you get some ideas, and I hope you enjoyed it a little bit. Right? I'll see you. See you next time.